For topic 7, we're going to look at products and quotients of complex numbers, okay? Now, if you're going to multiply or divide complex numbers in rectangular form, it can get kind of messy. It's sort of cumbersome algebra. Not necessarily impossible, it's just sort of a pain in the behind, okay? You might remember multiplying complex numbers, you would typically have to like do some foiling, or like what we call foiling when we're dealing with binomials. When you're dividing complex numbers, it involves like a special form of one where you multiply top and bottom by the conjugate of the denominator. They can get kind of a lot, okay? But luckily for us, if we're in polar or exponential form, we have a really easy way to multiply and divide complex numbers, okay? It just involves multiplying or dividing our values and then either adding or subtracting values for theta, okay? So given two complex numbers in polar form, okay, so we have z sub 1 and, whoops, we have z sub 1 equals r sub 1 times cosine of theta sub 1 plus I times sine of theta sub 1. So the little sub 1s just mean, hey, we're saying this is our first point, our first complex number. And then z sub 2 equals r sub 2 times cosine of theta sub 2 plus I times sine of theta sub 2. So don't get hung up in the ones and the twos. We're just saying, hey, this is the first point, this is the second point. So all we have to do to multiply these numbers is if we're going to take z sub 1 times z sub 2, we multiply the r's and we add the values for theta and then just plug them into regular polar form of a complex number. To divide the two numbers, like what we have here, we divide the r's and then we subtract the values for theta and just plug it into the regular polar form of a complex number. Now, with division, you do have to make sure that the second complex number, the one that you're dividing by, it can't be zero. That's fairly standard. We can't have zeros in denominators, okay? So again, with multiplying, we multiply r's and add thetas. I don't really think we need the apostrophes there. We just want, let's do this. We are many things. So far, we've discussed that we're not French. We're also not English majors, okay? So I don't know if I'm supposed to have apostrophes or not, nor do I really care, okay? Now, for the quotient, we divide the r's and subtract the thetas, and then we just plug them into that regular polar form of a complex number. Now, in the other column here, we have given two complex numbers in exponential form. So that's z sub 1 equals r sub 1 times e to the I times theta sub 1. And z sub 2 equals r sub 2 times e to the I times theta sub 2. So don't get hung up again in the ones and the twos. We're just saying, hey, this is our first point, this is our second point, and it's exactly the same thing. If we're multiplying, we multiply the r's and we add the thetas and then we plug them into the regular formula for exponential form of a complex number. If we're dividing the two numbers, we divide the r's and we subtract the thetas and then we plug it into the regular formula for exponential form of a complex number. So again, we multiply r's and add thetas, and then for the quotient, we divide r's and subtract the thetas. And the same thing here, we want to make sure that when we're dividing, z sub 2 doesn't equal 0. And we can't divide by 0, so that's fairly common to us at this point, okay? So the good news is these look terrifying. When you look at these formulas, you're like, oh my gosh, it's just like a lot. It's sort of like theta, r's, subscripts, just overload. But really, they're easy to use. We're just doing a substitution game. We're just plugging some numbers in and maybe doing a little simplifying, okay? So for example, 14. It says, given z equals 3 times cosine of pi over 9 plus I times sine of pi over 9, and w equals 5 times cosine of 5 pi over 9 plus I times sine of 5 pi over 9. Let's find the value of z times w. We're going to write it in polar form. And then we're going to find in part B the value of z divided by w, and we're going to write it in exponential form. Okay? So let's practice. Now, when we're multiplying, we want to take R1 and multiply it by R2. So let's say this is R1, let's say this is R2. So that's just 3 times 5, which is 15. Okay. I then take theta 1 and I add theta 2. Okay. Well, we're going to call this theta 1. So that means this is also theta 1. And then we're going to call this theta 2. Okay. So we're going to take pi over 9 plus 5 pi over 9. That gives us 6 pi over 9, which is going to reduce. Remember, 6 and 9 have a 3 factor that can be divided out. This is going to be 2 pi over 3. And now we just want to plug that into the following. Z equals R times cosine theta plus I sine theta. Okay. Now remember what we're technically doing is we're saying Z times W equals R1 times R2 times cosine of theta 1 plus theta 2 plus I times sine of theta 1 plus theta 2. We've already done the side work. We just need to plug the values into kind of like the OG formula. So we can say Z times W equals 15 is our R product times cosine of 2 pi over 3 plus I times sine of 2 pi over 3. And that's it. That's polar form. You want to keep the angles in there. You don't have to like evaluate sine and cosine. You want to leave the angles in there. And that's it. So it's really pretty easy. Just multiply your r's, add your thetas, and plug them into that original just polar form of the complex number. Now, for z divided by w, we need to divide. Okay, so we're going to take r1 divided by r2. Well, r1 we know is 3. R2 is 5, and that's all she wrote. It's not going to get any better than that. So then we want to take theta 1 and subtract theta 2. Okay, with division, you want to divide your r's and subtract your thetas. Okay, so we're going to get pi over 9 minus 5 pi over 9. That's going to give me negative 4 pi over 9. But keep in mind, we want to write this in exponential form. And we did have a condition on exponential form. So let's go up and let's talk. I don't think this one's going to be an issue. I think we might be okay, but let me double check. So right here, we do have to be in radians, so we're in radians. There's no real condition that this has to be positive, but we typically like to make sure that that theta value is positive. Okay, so let's go ahead down here. Don't want to scroll too far. There we go. Let's go ahead and find a theta value from 0 to 2 pi. Okay, so let's just take negative, let me write that a little better. Let's take our negative 4 pi over 9. Let's add 2 pi. That'll give us a coterminal angle, but it's going to be somewhere between 0 and 2 pi, so it'll be positive. Okay, so if my denominator is 9, 2 pi with a denominator of 9 would be 18 pi over 9. So I get negative 4 pi over 9 plus 18 pi over 9, which is kind of wacky, but 14 pi over 9. And that's what we're going to use as our difference, okay? So that is going to give us z divided by w. Now remember, z divided by w is r1 divided by r2 times cosine of theta 1 minus theta 2 plus I times sine of theta 1 minus theta 2. We've luckily already done our side work for the r's and the thetas. So we're just going to get z over w equals 3/5 times cosine of 14 pi over 9 plus I times sine of 14 pi over 9. And again, oh shoot, was anybody going to stop me? We're supposed to be doing exponential form. Anyway, we've got our polar form right here, but let's plug this into exponential form. So z over w is going to be 3/5 times e to the I times 14 pi over 9. And this is exponential form. So I guess lesson that we just learned here is answer the question that's being asked, okay? So make sure you do write this one in exponential form because that is what's being asked of you. So you just get extra points for doing polar. Okay, so next up, I think we have one more example. Yeah, we've got one more example of this. Okay, so given that z equals 8 times cosine of 40 degrees plus I times sine of 40 degrees, and w equals 2 times cosine of 20 degrees plus I times sine of 20 degrees, let's do the same thing. We're going to find z times w and then z divided by w. We're going to do the product in polar form and the quotient in exponential form. Okay, so let's see. This is r1 theta. Why'd I do a q? You can always tell it's getting late when dumb stuff starts happening. So we have theta 1, that's going to be this 40 degrees. And then we have R2 and theta 2 right here. Okay, so when we're multiplying two complex numbers, okay, that are in polar form or exponential form, we want to take R1 times R2. So we're going to get 8 times 2, which is 16. So that's going to be the R value that we're going to be using here. And then we want to take theta 1 plus theta 2, which is going to be 40 degrees plus 20 degrees or 60 degrees. Okay. And then remember, if we have z times w, that's going to be r1 times r2 times cosine of theta 1 plus theta 2 plus I times sine of theta 1 plus theta 2. We've already done the side work for the thetas and the r's, so we're just going to get z times w equals 16 times cosine of 60 degrees plus I times sine of 60 degrees. And that's it, okay? Now, we don't need to evaluate. If we were to evaluate, that would get us to that rectangular form. We are not being asked for a rectangular form of a complex number. We just want the product of two numbers that are in polar form, okay? Now, find the value of z divided by w, but we're going to write it in exponential form, okay? So let's see, r1 divided by r2. Well, r1 is 8, r2 is 2, so we're going to get 4. Okay, and then theta 1 minus theta 2. Remember, for division, we divide r's, we subtract thetas. Theta 1 is 40, theta 2 is 20, so that gives us 20 degrees. Okay, and then we are going to go to exponential form, and that's going to be r1 over r2 times e to the I times theta 1 minus theta 2. We've done the side work, so we can just say z over w equals 4 times e to the I over 20 degrees. And don't get too cocky and confident. Tap the brakes. Is there something we remember about this? And the something that we should remember about this is when we're dealing with Euler's formula, which allows us to write complex numbers in exponential form, we do have the condition that everything needs to be in radians. So if we need to scoot back a bit, quite a bit. All right. So this Euler's formula that is the heart and soul that allows us to write a complex number from polar form to exponential form, we do have the condition that everything must be measured in radians. So the answer that we have down here with the 20 degrees, it's not going to quite work for us. We need to convert the 20 degrees to radians, but luckily that's something we did way back in 7.1. So if you have degrees and you want to write it as radians, you would multiply whatever your degrees are by pi over 180. That's just it's a weird form of one. Okay, you can call it a well-chosen one, which is really fancy. It's just a weird form of one. I know that 20 degrees divides into itself one, and it divides into 180 9 times. So we could say that 20 degrees is really pi over 9 radians, and this is what we need to use. So we're going to take this right here. We're going to say, okay, z over w equals 4 times e to the I times pi over 9 radians, and then we're good. Okay, so you do need to remember that little caveat. To do exponential form, we really do need radians. Okay, so that's it. That is multiplying and dividing numbers that are in polar form or exponential form. Pretty easy. It's really just multiplying or dividing r's, adding or subtracting thetas, and then plugging them into a formula. Okay, one more video, and then we've got another section behind us.